In today's lesson, we are going to start talking about inverse trig functions. We're going to begin our lesson with a little bit of a review from Algebra 2. So a couple things that we focused on quite a bit in Algebra 2 were the idea of domain and range and inputs and outputs. So with domain of a regular function, that was the x values, and range would have been our y values. Now with our trig functions, that's not exactly the same thing. With our trig functions, the domain are going to be the angles, and the range is going to be the ratio associated with those angles, such as y over r or y over x. Any function, each input only has one output. So what that means is that if I asked you, for example, to find the sine of pi thirds is my input, and there is only one ratio associated with pi thirds. That is why sine is a function. And we say that all functions pass what's called the vertical line test. Now, an inverse function is going to undo the original function. This is not the same thing as a reciprocal. When we find an inverse function, the domain and the range switch, and any point that was on my original function now has the x and y coordinates flip-flopped on the inverse function. So before, when we used to graph points, they were of the form angle ratio. On the inverse function, those points will now look like the ratio, comma, the angle. So when exactly does an inverse function exist? Because they don't exist everywhere. In order for a function to have an inverse, it has to pass the horizontal line test, which I will abbreviate HLT. And if the function happens, if the original function passes the vertical line test and the horizontal line test, then we call this function one-to-one. And when a function is one-to-one, it means that each x goes to only one y, and each y goes to only one x. Now, if we think about this in the trig world, that would mean that each angle has one ratio, and each ratio has one angle. And right now, there should be some red flags going off in your mind, because we know that as we travel around the unit circle, that those ratios that we get are associated with more than one angle. And that's where we get to our last point here. If a function fails the horizontal line test and is not one-to-one, such as our trig functions, then we can restrict the domain so the inverse exists over a limited domain. And you might recall we did this back in Algebra 2 when we were working with parabolas and square root graphs. We would say, for example, I have only half of a parabola, so that then I could go ahead and find its inverse. Okay, so how is this going to relate to trig? Well, if we were to try and solve these equations that we see here and find the angles that have a sine ratio of root 2 over 2 or a cosine ratio of -1/2, we would have a lot of answers. For example, angle A, this ratio would be true when angle A is pi fourths or 3 pi fourths. Now we can go around the circle and get 9 pi fourths, 11 pi fourths. We could go backwards around the circle and continue, and there are an infinite number of angles that have a sine ratio of root 2 over 2. The same thing is true for cosine equaling -1/2. To make this equation true, angle B could be 2 pi thirds. It could be 4 pi thirds. We could travel around the circle again and get 8 pi thirds, and so on. So the functions sine and cosine are not one-to-one, okay? And they are not one-to-one because each ratio has more than one angle. Oh, that's kind of confusing. More than one angle. If we were to think of this visually, think back to how we drew these graphs. When we learned how to graph our sine curve, it looked like this. Well, does that graph pass the horizontal line test? No. I can draw a horizontal line right here, and it crosses my graph more than once. So we can also say it is not one-to-one because it fails the horizontal line test. All right, so what are we going to do with this knowledge? let's take a look at how we can restrict the domain for these functions. So this is my current graph of sine of x. Now what we want to do is we want to restrict the graph so that we have every ratio value possible with no repeats. Now that means we need to include the ratio values that are positive, that are negative, and 0. So if we look at this graph, we can go ahead and we can say, well, let me get my highlighter here. We can say that for this section of the graph, this will include negative ratios, positive ratios, and the 0 ratio. We want to make this section of graph that we picked to be as close to the origin as possible, and that's why we go with this section right here. Now, if you recall our graphing, this was negative pi halves, and this was pi halves. So what that means is that our restricted domain will be angles from negative pi halves to pi halves. Now, when we go to graph this, it's often easiest to just write the points and then flip-flop their coordinates. So if you think back to our graph y equals sine of x, if we were to write these three ordered pairs, so we had our x and our y, which we can also think of as our angle and our ratio. When our angle was negative pi halves, y was negative 1, 0, 0, and pi halves and 1. So now when we go to do our inverse function, y equals sine inverse of x, now we are essentially going to flip-flop those x and y values. So now my input is going to be a ratio, and my output, or my y value, is going to be an angle. And so all of these ordered pairs essentially flip. All right, so right here we are flipping the x and y values to graph the inverse function. All right, now when we graph this, this is going to be called, and sometimes this will be called the arc-sine graph. I typically call it the sine inverse, but you should be able to recognize it in both ways. You will see it both ways on your worksheets and in Math Excel. All right, so we're going to go ahead and graph. We're going to label our x-axis, negative 1, 0, and 1. Label our y-axis, negative pi halves, 0. Oops. That's the negative one. This is the positive one. And then we'll go ahead and we will plot those 3 points. And then we will draw in our curve. Now, a couple things that are important to remember. This is not a straight line, okay? I know it might look like with those 3 points that it would be straight, but it is not a straight line. I kind of think of it like the graph is going to curve towards, can't spell today. It's going to curve towards, all right, really? The y-axis. It's like my brain was jumping ahead to the next thing I was going to write. All right, you will be expected to have these graphs memorized and either be able to pick them out from multiple choice or recreate them on your own. All right, let's go ahead and take a look at our cosine graph. So for our cosine graph, same idea. We want to pick an interval of the graph where both positive and negative ratios are represented, and we want to be as close to the origin as possible. So if we look at this graph here, the cosine graph can't use the same interval as the sine graph. If I were to use that same interval and go from negative pi halves to pi halves, that would only give me positive y values. So that's why we end up using a different interval, and we end up using the interval of 0 to pi. And these are the 3 graphs, or 3 points that we are going to look at. All right, so if we did the same thing and made our t-chart, y equals cosine of x, y equals cosine inverse of x, also called arc cosine of x. Make our t-chart. Remember that this is an angle giving us a ratio as output. For our inverse graph, the input is a ratio giving us an angle as our output. All right, so these 3 points for our cosine graph have angle values of 0, pi halves, and pi, and y values of 1, 0, and -1. And we can flip-flop both of those values to get the ordered pairs for our inverse graph. And then when we go ahead and graph this function, we will label our x and y values. And then notice all of our y values are positive. So this graph doesn't have anything below the y-axis in this scenario, and that's because all of the y values, which are angles, are positive. All right, so when x is -1, the ratio is pi, 0, pi halves, and then 1, 0. And again, just like with our sine curve, this graph kind of cups a little bit towards the y-axis, looking like this. And again, you will need to memorize this graph. All right, so what does this mean? What this means is whenever you are asked to find an angle for sine or cosine, we have to keep these intervals in mind, okay? So if we look at these given problems here, a sine inverse of x will have an angle in the values of -pi halves to pi halves as its answer, and a cosine inverse of x will have an angle in 0 to pi as its answer. So basically what this is doing is it's restricting our domain so there's only one possible answer. So when I see this first question right here, what you want to think of when you see this problem is, what angle in -pi halves to pi halves has a sine ratio equal to 1/2? That is how you want to be interpreting that question. So we say, okay, where does sine equal 1/2? Sine equals 1/2, reference angle of the 30, and in radians, that would be pi 6. And there we go. That's the only acceptable answer here. I understand there are multiple angles that have a sine ratio of 1/2, but in order for the function's inverse to exist, we have to limit the possible answers to just one. And there is only one answer in the -pi halves to pi halves window. All right, same idea for cosine. When we are reading our cosine problem, the way we want to see this is what angle in 0 to pi has a cosine ratio of 1. And we'd say, okay, cosine equals 1 at 0, so my answer here is 0. All right, pause the video and try the next two on your own. Okay, for our next problem, where does cosine have a -√2/2 ratio? Again, we know that cosine has to be in our 0 to pi window, therefore this has to be the answer in quadrant 2, which should be 3 pi 4ths. Now the last one for sine is one that people frequently miss. Remember, we are looking for an angle, and that angle has to be in the values of -pi halves to pi halves. So visually, a lot of people often recognize that it needs to be the right side of the graph, and they recognize that it needs to be somewhere on this side of the graph. And then they'll say, oh, okay, so then it's going to be this angle right here, therefore it's 5 pi thirds. Well, the problem with that is that 5 pi thirds mathematically does not fit in that interval of -pi halves to pi halves. It's not in that list of numbers. And that's why we have to find the equivalent angle that is in that list of numbers. And -pi thirds is mathematically in between -pi halves and pi halves. All right. Tomorrow we will discuss the tangent graph, and then we will also talk about the domains and ranges for the other three functions.